Okay, so everybody can hear me? Would you say yes in the chat box? Okay, so thank you very much. And what about the others? Okay, good. So, right, let's wait 1 minute and start after 1 minute. Okay, so let's start today and share this. Okay, so where we are. So we are, I hope all of you have a great vacation. And welcome back to the lecture for the CS520. And here's a quick reminder about what we have done so far. So we studied about program logic that allows us to specify properties and properties about imperative program formally, and also allows us to prove those properties are indeed met. So we found there's something that's called for logic for partial correctness. And we studied some mechanism to specify program using triples. That was the partial correctness specification. We also talk about total correctness specification, but it's not going to be the focus of this lecture. The lecture, yes, one lecture before and then today's lecture. Textbook talk about total correctness as well. And then we also talked about some proof rules for showing the satisfaction of specifications. And also what we did was we look at one example, which is using divide by 3. And we looked at some proofs about this. Then in that example, what I emphasized quite a bit, so it's a property of divide by 3, is that the key part of the proof is involving specifying so-called the loop invariant. And then again, I pointed out 2 exercises. One exercise is about coming up with a different proof for assignments. And the second was the proving correctness of 2 programs. One is about factorial, Fibonacci number. The second one was about the Euclid algorithms. So what we're gonna do today is to solve these exercises, and then we will also look at the soundness of the proofs. So we talk about these proofs, but who knows, maybe these proofs may be completely wrong. So we have to have a way should justify these proofs. If we use them, indeed we have a proof about programs. So we need to show the sometimes called soundness or sometimes called correctness of these proofs. And we're gonna use denotation of semantics to prove this. So the first part of today's plan is to do this. The second, and solving some exercise. So that's going to be the first part of today's lecture for this chapter. I think it's chapter 3 or chapter 4. So let's look at the exercise. The first exercise was to come up with a proof word that help us to see the proof word in Hoare logic as forward symbol, forward execution. So I said that the one kind of heuristics that I encourage you to use when you prove programs using Hoare logic or proofers in Hoare logic was thinking about running program backward. Okay, and so that process allows you to. I mean, the key step in that process is to use the assignment rules. And the typical assignment rule you will learn looks like this: the post condition Q. So, and then usual way to read this is given a post condition Q, if you have an assignment, you can, in a sense, run program backward with respect to the post condition. And the outcome of running program backward is essentially replacing all the occurrences of X inside the Q by expression E. Okay. So that's the proof for the assignment. The so-called sometimes called backward rules. Then there's also forward rule. Okay. If you're given P, and then the forward rules say, if you have an assignment like this, then it tells us what should go into the output. Should be the post condition. The post condition, the forward rules say, should look like this. Use a different color. So it say that we should talk about introduce some existential quantification. And the core of this existential quantification is to talk about the old value, because after the assignments, in the final state, the old value of X is not going to be available. But if X appears expression E, as well as if X appears inside the precondition P, they refer to the old value of X, not the new value, okay? So we should say, talk about this old value, should have some way to talk about this old value. And then in the forward rule, it uses existentially quantified variable to talk about the old value of variable X. So it said there exists X0, which in our intended usage, X0 should denote the old value of X before the assignment. And then we have an equality because of this assignment, okay? But inside the equality, if X appears inside the expression E, then that X should refer to the old value of X. So we should apply the substitution here. Okay, so we say X is equal to E, where every occurrence of X inside E is replaced by old value X0. And then we also should say precondition continue to be true, but if X appears inside the precondition, that should refer to the old value of X. So we also apply substitution like this. So if you think about this, this interpretation is not super surprising. I mean, we just said we introduce existential quantifier to refer to the old value of X. And then whenever the expressions or assertions should talk about the old value of X, we should use X0 instead of X. So that's the intuition about this rule. It turns out this is the best, in some sense, post condition we can get. So that is sometimes called strongest post condition. This is the best post condition we can get. And many of the automated theorem prover uses either this backward rules or this forward rules. I mean, inside its implementation. So that's a solution for the first exercise. Solution for the second exercise was to show prove the correctness of Euclid algorithm. So the Euclid algorithm looks like this. So I write the quadruple specification. The specification said we have input A and B. A is greater than or equal to 1, B is greater than or equal to 1. And then we store the value of A to some auxiliary variable, but in textbook it's called ghost variable, which is not used by the program. And B, we say is equal to B0. So these A0, B0s are some variable that intended to store the initial value of A and B. And then Euclid algorithm, what it does is that it computes greatest common divisor between A and B. In Korean, it's called 최대 공약수 between A and B. Okay. And then implementation looks like this. Say that if A and B are different, so if A and B are not equal, we do the following. We compare we try to find something bigger between A and B. So if A is bigger, then we reduce A by B. Otherwise, because A and B are different, in this case, B is going to be bigger than A. In this case, we say that B should be equal to B minus A. And that's the algorithm. Okay. If we do so, then what we get is that the post condition is in A is going to be the greatest common divisor of A0 and B0. So the A stores the greatest common divisor of A0, B0. And that's the algorithm that you perhaps learn in the algorithm course. And now the question is, how can you prove this using Hoare logic? And then the proving this in Hoare logic, the key step is to identify, because it has a while loops, we should use the proof rule for the while, which looks like this. We say that we have to find the invariants, and if we have a while, B, C, not to C, then what we have to do is that we have to prove invariant is preserved by the loop under the loop condition. Once you do it, then we can conclude that invariant is going to be true after the while loops. And then another thing we know is that loop condition is going to be false. Okay. So then to prove this program, the key step is to identify the invariant. Okay. What I should be in this case. So the invariant in this case is going to be following. So invariant to say we have a greatest common divisor of A0 and B0. It's the same as greatest common divisor of A and B. And in fact, this relationship is the key property, or in a sense, key idea behind this algorithm. And then A is always greater than or equal to 1, and then B is also greater than or equal to 1. Okay, so that's the key idea of this algorithm. Now, and then this loop invariant captures this key idea, and then how to prove this. And we use this proof rules. So first, we have to show that, to use this while rule in this context, what you have to do is that let's call the entire thing as a precondition P, and this entire thing as a postcondition Q. So then the first thing we have to do is that we have to show assume that the invariant somehow work out, and then we have to show that this invariant is good enough. Okay, what does that mean? This means that using the proof rule, the Hoare triple for while with this invariant, and if we use a rule of consequence, then we can prove this entire triple. So what we have to show is that we want to prove P this Euclid, Q is going to be true. So this is our goal. And then in the proof, we use a rule of consequence, which say P should imply I. And for the while loops, we want to use rule for while. Okay, so, and then what the conditions for the while is A is not equal to B. So we put a negation, I, and negation of not A is equal to B, which means A is equal to B, right? And then we have to show I, this post condition. This implies the post condition Q. Okay, so what we have to do to complete the proof is to check whether this implication is true. And then we have to complete the proof of the while. And then we also have to check the loop invariant together with the negation of the loop condition implies the post condition. And then first, which is say A is greater than or equal to 1, B is greater than or equal to 1, A is equal to A0, B is equal to B0. That obviously implies this loop invariant I, because I mean almost everything is the same, except that instead of saying GCD of A0, B0 is equal to GCD of A and B, the preconditions say A is actually equal to A0, B is actually equal to B0. So this first part, which is P implies invariant I, is true. Okay, it's very easy to see. And then the part 3, okay, say that if I and negation of A is not equal to B, this means A is equal to B. Okay, so what does this tell us? We have an invariant, and in particular, one part of the invariant tells us greatest common divisor of A0, B0 is equal to greatest common divisor of A and B. Furthermore, we know that A and B are the same. Okay, if A and B are the same, their greatest common divisor is exactly the same as A. So one thing is that greatest common divisor of A and B, if A and B are the same, then their greatest common divisor, 최대 공약수, is A is equal to A. Okay. So this, I mean, this part of the invariance, and then the other part, which say A is equal to B, they together implies greatest common divisor of A0, B0 should be equal to A. Okay, that's exactly the post condition that's written here. So the step 1 is done, step 3 is done, and then the remaining step is to show the invariant. And then proving the invariant part goes like this. We follow the rule for while. The while rule says to show something is an invariant, we have to show that the body of the loop preserves the invariant under the loop condition. So what we have to prove here is the following. Say invariance and the loop condition, which is A is not equal to B. Under this condition, the body, say if A is greater than B, then A becomes A minus B, else B becomes B minus A. That's going to reestablish the loop invariant. So now another thing we learned last time is the proof for if then else. Proof for if then else say, if you want to prove something about if then else, you have to prove something about the true branch and the false branch. And then when you prove something about the true branch, we can assume that the loop condition, that the condition of the if then else is true. When we prove something about the false branch, we can assume that the negation of the condition is going to be true. So we have to show I and A not equal to B, and the loop, this condition of the loop, under that conditions, A minus B is true. And this is what we have to prove for the true branch. False branch, AB, and then it's negation of the loop condition. B becomes B minus A, I should be true. And then proving both branch is essentially very, very similar. What we do is we use this time I'm gonna use the backward rules. So if you use the backward rules, we have for the assignments, we have I where A becomes A minus B. So this comes from the backward rule for assignment. And then we have to show I and the negation of B and greater than B implies I where A becomes A minus B. But if you actually apply the substitution, proving these implications or checking this implication boils down to the following property. If you have a greatest common divisor, I think this is better. If A is greater than B and B is greater than or equal to 1, so then what's true is the greatest common divisor of A and B, same as greatest common divisor of A minus B and B. And this is a key idea behind the Euclid algorithm. And then if you use it, you can complete the proof. You can check this implication is going to be true. Formally speaking, you have to use some proof rules for showing this implication, and that's what's being done by automated theorem prover and automated program verifier. But in this exercise, if you just check and convince you this implication is true, that's good enough. Okay, this is the second exercise. And now let's move to the next topic, which is the soundness. What the soundness means is that proof rules. It means the following. Say that lemma. It says that if we prove PCQ in while logic, so which means that using the rules like rule for assignment, rule for if then else, rule for while loops, and rule of consequence, and so on. So then what triple PCQ is valid. So this validity means the following. If you take the semantics of PCQ, that's going to be true. That's what this is saying. Okay. So what this just tells us is that the proof rules are okay. If you use them, you will never prove something wrong. All the things that you prove are going to be true. So then the question becomes, okay, this is a kind of assurance that we want, right? If the automated prover, which is based on while logic, or automated verifier or program verifier based on while logic, if it claims to prove some property, but at the same time, it turns out what it claim is wrong, and that's not what we want. Okay, and then this soundness, just assures us that that kind of thing will never happen. And it's actually the first step that if somebody come up with new proof rules for verifying programs or automated verification techniques, they have to prove something like this lemma. And then question becomes how to prove this. Proving this lemma, but sometimes maybe theorem is a better word. The Soundness Theorem have almost in all cases follow the same pattern. The pattern is that if all the proof rules are correct, so this is the what's gonna be proved by this in the soundness proof, the proof of this theorem. Okay, what does this mean? This means that if we have a proof like V1, which looks like this, V1, V2, Vn. So each of the VI's can be quadruples or implications between two assertions and so on. And then we have a conclusion V. If this we have a proof of this form in our logic, which is then is one of in our logic, then the following is true. Then we have the implication. If V1 is true, V2 is true, and so on, and Vn is true. That implies the conclusion is also true. So this means that if we construct a proof that derive a certain quadruple using proof rules, then eventually that derivation will not have any assumption. All the assumptions will be derived by some rule. And this the correctness of every rule in whole logic ensures that what you derive is going to be always true. So the proving this correctness of each proof rule is a way to prove this soundness theorem. So I want to cover two rules in this lecture, but before, I think the best way is, for you to spend some time to think about how to do the proof, then I will give you an answer. So here's two proof rules we want to think about. The first proof is a rule for assignment. So we have a backward rule for assignments, Q. Then we have a rule for while. Okay. While loop is, and then you will also see that while trying to prove this rule, and you need to use because everything is in terms of denotation of semantics, you need to use the denotation of semantics. And then see some aspect of denotation of semantics in the proof rule. So the exercise is to show the correctness of these rules. So I will give you, 3 minutes to think about this. Actually, 4 minutes. Okay, so let me show you how to solve them. So for first question, we have to show the correctness of this rule. Q is going to be true. And what does this mean? This means that whenever for all, say the same thing as for all state sigma, if the state sigma satisfy the precondition, so then so I'm gonna use some notation, which is then we'll have the following: Q lifted. So this notation means, this lifting notation, this Q is an assertion. So what it does is that it takes states and returns Boolean. And we lift them using bottom. So if you lift them, that's going to be a function that maps state together with potentially bottom, and it returns Boolean together with bottom. So this Boolean is the domain, which look like true, bottom, and false. So then this has an order relationship, and the order relationship say the bottom is smaller than true, also bottom is smaller than false. And then that this I wrote there, say given if the state sigma initial state satisfy the precondition, then when you run the command under the states, we may either have a bottom. In that case, everything is okay, because if it's a bottom, then this Q lifted will return bottom, and that's going to be less than equal to true. So everything is okay. Otherwise, we're gonna check Q is true or false. If Q is true, but Q should be true, because true is only less than equal to true itself. Okay. So, beforehand I said this, what triple say, initially if the initial state satisfies the precondition, if program terminates, post condition has to be true. And what I wrote here is a way to write exactly the same thing using the order relationship. And that's gonna be convenient to solve the while loop case. But in this case, things are a bit simpler because assignment always terminates, and we know it's even outcome. So this whole thing, in this case, is going to be sigma, where x is gonna be updated to the value of expression. And then because it's a state, we have, that this entire conditions say that the Q should be true under this state. Okay. So let's look at what does this tell us. It tells us if Q x e sigma is true, so then the Q sigma x, this has to be true. But although I don't expect you to remember the substitution lemma that we talked about before, I hope you get some sense that this looks like talking about relationship between two substitutions. Here are the syntactic substitutions where we apply the substitution on assertion Q. Here are the semantic substitutions that we apply the substitution on the sigma. So in fact, we learn about substitution lemma when you study predicate logic. And in particular, one of the corollary of the substitution lemma said, if we apply the substitution, that's same as applying the substitution on semantically. So this is what we learned before. And because this equality is true, I mean, if one side, the left-hand side of the equality, that's exactly this precondition part, that's true, then the right-hand side also has to be true. And in fact, this, I mean, we have a much, this substitution lemma says something much stronger. It says that if the Q where X is replaced by E, so the precondition in the assignment rule is false, then the post condition is false. That's not required, but that is something much is also follows from the substitution lemma. Okay, and because of this, I mean, this assignment is sometimes the outcome, the precondition that we obtain from the assignment rule is sometimes called the weakest precondition. But just the point I'm making is that here we have a proof rule for assignments, but that is closely related and in a sense follows from substitution lemma that we studied before. Okay, so that's the first case. The second case is more complex. So just like I said before, to show the conclusion of the while rule, which is I while B to C, I and negation of B is true on the, I mean, this is true. Showing this is equivalent to show for all state sigma. So we have sufficient to show that for state sigma, if I precondition is true, then the post condition lifted is going to be true in the semantics of for the post state, I mean state after running the while. Modular if it terminates. Okay, so this is the relationship that we wrote. And then to prove, while proving this, we may assume, because of the assumption, that something similar is true for the body of the loops for sigma state. If invariant but the condition of the loop is true, so then invariant is bottom body of C sigma is equal to T. And this is coming from the assumptions of the while. This part is coming from the assumptions of the while rules. This part is an obligation that we have to discharge. That's coming from the conclusion of the while. Okay. Just to give you a reminder, I mean the conclusion means this guy, assumption premise or assumption means the one that I just marked. Okay. So then how to do this? Okay. To prove this, we just use the denotation of semantics. So I mean, but first we start with the, I mean, for every state satisfying the invariant. So we start with this state satisfying the invariant. So we pick sigma such that the invariant is true. Okay, let's not do this. So what we do, we first simplify, we unpack the definition of this while. And what's this definition? The definition said it's fixed point applied to some operator f, where this operator f is defined like this. It takes, it lives in the, it takes a semantic command and then return semantic command. So continuous function. But here's a take only continuous functions. And then if it takes a semantic command and initial state sigma prime, it first check whether body, the loop condition is true on the sigma prime. If that's the case, it run the body of the loop once on the sigma prime, and then run the f, the parameter f, which is represent the what's going to happen after the one iteration by this loop. Okay. Otherwise, if the loop condition is false, we just return sigma prime. Now, this is the operator capital F, and this y is a least fixed point operator. But if this y of f, we learn that's going to be so the list of fixed point is always defined like this. So limits, I mean list upper bound over some chain, which we create by applying f to the bottom. So here, bottom means semantic command that takes any state sigma prime and return this bottom which lives in sigma. I mean this bottom lives in sigma to sigma bottom. Okay. So this is what we have to prove. So we plug in our things that we have to prove and just look at what our proof obligation actually look like. So this is proof obligation. If we plug in what we have to prove there, this obligation look like this. We say I and negation of B bottom, and then n is equal to 0 infinity, Fn bottom, that apply to sigma that is less than equal to t. But now this Fn, this whole thing, it lives in semantic command. So it lives in this domain. So we said in the function space, the list upper bound is defined pointwise, which means that the list upper bound of a chain applied to some state. This is the same as taking the list upper bounds, but instead of computing list upper bound in the function space, we compute list upper bound in the result space. So for each Fn bottom, which is a semantic command, we apply the semantic command to state sigma. And that's, so this is the, right. So the one above is same as the one below. But then, although it's very easy to show, but if you can prove that this operator, that's a lifting of the assertions, is always continuous. Okay, it's always going to preserve the limits of increasing chain. So this whole thing is equal to n is 0 to infinity, where equation of B Fn bottom and sigma. Okay, this is less than equal to t. Right. So okay, so this is what we have to prove. Now, to show what we have here, what we need to prove is that t is greater than the least upper bound of this chain. So this whole thing can be proved. So this is implied. If we show that for B, What does this mean? This means that the true is an upper bound of the entire every element in the chain, and that's gonna be an upper bound of the least upper bound of this chain. Okay, because right, so this is what we have to prove, and we can prove this by induction. So I'm not going to prove the whole thing of the induction, but I will show you perhaps the most difficult part of the inductions. So to prove this as an induction, we now do the following. We pick sigma that satisfy the precondition, which is invariance sigma is true. And then we're gonna show that if for every sigma this invariant is true, then okay, let me just clarify what's going on. So what we are proving by inductions, so here's what we prove. Is for n greater than or equal to 0. And the following is true for or state sigma if precondition is true. So then things that I wrote there, I and relation B, bottom Fn sigma is less than T. And this is what we're going to prove by induction. Okay, so we can do the induction on n and then prove this. So base case n is equal to 0 is actually very easy. So I'm going to only focus on the inductive case. And we have to do case analysis. So I encourage you to look at the lecture notes. And there is a complete proof about the inductive case. But among the inductive case, I'm going to consider only the most difficult, challenging one. So the most challenging one, to prove the inductive case, we have to pick sigma such that n states that this I sigma is true. Then we have to do case analysis on sigma, but I'm gonna only consider the most difficult one. The difficult case is the following. Case is that sigma the loop condition is true on the sigma. So we go into the loop, and so this is one of the cases. The condition is true, and then when you run body of the loop, so C is the body of the loop. On the sigma, it's not going to be bottom. Okay, so there are cases where the loop condition is false. Also, there's a case where when you run the body of the loop, it's going to be bottom. But this is the most difficult case. So in this case, how we can take care of this? Okay, so to prove this case, we unpack this definition. So we look at what we have to prove. Is invariance on the negation of B bottom has to be true for all Fn sigma. We have to show this is the case. Now we do some calculation on the left-hand side of this inequality. The way we do it is we use the definition of this Fn. So this means F applied to sigma. Yeah, so if fn bottom means, apply fn times, so we just apply f to n minus 1 times and then apply to sigma. And that is same as, if you look now, give the definitions of f. So I plug in the definition of f. It goes like this. You say that if the Boolean condition is true, if that's the case, then we run f with its not run f. We first run the command C, the body of the loop with state sigma, and then we run its argument, which in this case fn minus 1. And it's lifted version. Otherwise, we just return sigma. So that's the just plug in the definition of f, but by assumptions of this case, the condition of the loop is true, and then the outcome of running C on the sigma is not equal to bottom. Okay. What does that tell us? Then we only get this branch because the condition is true, and also the command part is a state, not a bottom. This whole thing is going to be the same as just fn minus 1 bottom C of sigma. So if we just plug in just implement what we have just discussed, this entire thing is going to become like this. So at this point, we want to use the induction hypothesis with respect to f and n minus 1. But to use induction hypothesis, we need to know state that we are giving here, which is not sigma, but command C applied to sigma. We have to know that this guy actually satisfies the invariant. So if you compute the invariant here, if the answer is yes, then we can use the induction hypothesis. If no, then we got stuck. We don't have anything. Okay. So then what should we do? Then why we have this this yes? So actually we have a yes case here, and the reason is because of the assumptions or premise of the while loop. If you look at what's really happening here, we have this Boolean condition is true, and also if the Boolean condition is true, and then also because the state sigma is starting from state satisfied the precondition, the invariant is also true. So that is I and B is true on the sigma. And then if you go back, so the assumptions that we can make in the proof is this case. So we said for every state sigma, if the state satisfies invariant as well as loop condition, then running the body will produce either running the body, if it terminates, it's going to satisfy the invariant again. Okay. So this is the assumption that comes from the premise of the if then the while loop, the loop for the while. So if we just plug this in, then by that assumption, we know running the command C, let's write it exactly. I lifted command C on sigma is going to be less than or equal to T, but this part we know this is not going to be equal to bottom. So the whole conditions here, this implies I, this sigma is equal to true. Okay. So that completes the proof. So we can apply the induction hypothesis. I mean, that take care of this question. So then if we apply the induction hypothesis, then we are given a state to Fn-1 bottom, but then given state satisfy the invariant. So the entire thing is going to be less than equal to true by induction hypothesis. It's a bit complex, but the overall structure of the proof is not that difficult. It's, I mean, say what we have to, we write what we have to prove in terms of this order relationship. And then we plug in the definition of semantic definition of the while rule. So what we have to prove is rewritten in terms of this fixed point, the explicit representation of this fixed point. The explicit representation of this fixed point. And then we use a continuity to move the least upper bound out. And then we wrote what we have to prove in terms of just each of the elements in the chain that arises in the least fixed point. So that is what we obtained here. And then we use induction to complete the proof. Okay, so I encourage you to look at the proof of this while rule. I mean, while rule is very important, but at the same time, you get a sense about how to use the semantics to do something useful. Okay, so before moving on to the next part, that's it for this chapter on the program logic and specifications and proof for imperative language. If I'm gonna wait for like 1 minute. If you have any questions, it's time for you to ask me. Okay, so I will assume that there are no questions, so I'll move on to the next part, which is, actually I didn't write it. It's a chapter 5. No. This is a chapter 5. Actually, it's a chapter 6. It's a bit strange. Okay, so what's the next chapter? So far the next chapter in the textbook is about, so we're gonna skip the next chapter, which is gonna be about, verifying programs that uses arrays. And then we'll move on to the one after. And that chapter is about the continuation and the input, output, and continuation. Well, you can say more realistic features of programming languages. So what's the motivation of that chapter? Right, just write a title. So failures, input, output. And continuation. It's a chapter, I think 6 of the textbook. chapter 6. I think it's actually chapter 5. So what's the motivation of this chapter? High-level message. So motivation or high-level message of that chapter is that we want to study programming language with more realistic features. And typical features that arises in programming languages are input and output. So without input and output, you can't do anything interesting in programming languages. And then also there are most of the programming language support gives you something that allows you to change the control of the execution. So, and in C, there is something called exit. Also another thing that appears commonly in programming languages is goto. And more sophisticated form of goto is continuations in like rockets. There's something called core CC. And other languages, another way of changing the control is done by so-called exceptions. Okay, so exception, continuation, and so on. These are the primitives, constructs in programming languages that allows you to change the control of the execution. Then so what we're gonna do is we'll study consider the simplest form of this control operator called failure, and then we will study about develop mathematical tools that allows us to analyze this feature. So that's one aspect of this chapter, and so which are going to consider input, output, and failures. But in doing so, we will learn some important mathematical tools. The one important mathematical tool is so-called recursively defined domain. And it's more sophisticated than the simple domains that we studied before. And it's a bit like a fixed point, but not on the level of elements, but on the level of space. But in doing so, one thing that pops up in this solution of this recursively defined domain is a different perspective, or more deeper understanding about what domains in domain theory, what pre-domain in domain theory actually means. So this may give you some new perspective or deeper understanding of domains and pre-domains. In particular, the specific view that I'm gonna emphasize quite a bit while talking about this recursively defined domain in this context is that elements in the domain represent computation, not just an outcome of the result. So, but it represents computation. So elements of pre-domains computations in abstract form. So beforehand, we said the command is a mapping from state to state bottom. So in a sense, this outcome already represents the computation, which is either producing the final result or doesn't produce anything. So bottom means doesn't produce anything, And then the other case, element in the sigma means that it terminates and produces some output. But in this section, we will consider much more sophisticated computation. So it's a bit like representing computation in a very abstract, concise form with lots of details just disappeared, like filtered out. But in this case, we will study something where a bit more intermediate steps of computation are included in the definition of the domain, this output domain. And then the third one, so we will also study the notion of continuations. This is, very important in the language design as well as the semantic tools. And also, this continuation appears quite a bit in some form in so-called dual space in mathematics. Okay, so that's what we're gonna do. So remaining 5 minutes, I'm gonna tell you what kind of language we're gonna consider. So the syntax, so I'm actually talking about this. There's actually one more thing I want to talk about is that I said the most important part of the denotation of semantics is the semantics of a command type. So if you just, I said if you look at the semantics of interpretation of commands, there was a mapping from state to state pattern, okay? And then interpretation of expression, integer expression was a mapping from state to integers. And I said that form, or I often call this as a semantics of command type, semantics of the expression type. But you can think of this as a the shape of the semantics. And this tells quite a bit about what's really happening. And I said, when this shape changes, that indicates the major change in the language design. And then you will see that this shape has to be changed if we start to include exceptions and the failures and input and output. And that also get mirrored by the fundamental change that's happening in the language. Okay, what's the syntax of the language that we're gonna consider? Integer expressions and the Boolean expressions are going to be the same as before. But for commands, we will have a bit more. So commands, we have the same thing as before. I've just included one case which I didn't perhaps emphasize it that much, but we also had a new variable declaration. It's often written this way. Okay. Expression and command. Then we will look at a few more cases. The first case is a failure. You can think of it as an exit in C-like languages, or you can think of it raising an exception which will never be caught in Java. Okay. So failure means stopping execution. And then we will also consider two more commands. One is output. So this bang means we're gonna produce an output. And we will output integer expression. And then we will also take an input from the user. So this question mark will be an input from the user. And then we will provide a variable that will store the value. Okay. So that one, I think the best way to appreciate or understand this syntax is actually look at some example programs. So here's a very simple example program. So we declare, for example, say x becomes 124. And we go to the infinite loop. But instead of don't do anything, this loop interact with the user. And the interaction is it takes input from the user and store it y. And then if y is not equal to 0, y is equal to 0, then it stops. Okay, it failed. Otherwise, it divides x by y. So this y division is an integer division. And then it produces x as an output. So this whole thing is the loop body, and this program runs forever. Okay. So if you do the interactions, then user may see that if you user plug in, say 2, that's an input, then corresponding output is going to be 62. Then if you plug in like 2 again, 4, as an input, then the output is going to be 25 because of the integer division. And then if you plug in, user plug in 0, then program will terminate. Okay, so that's the kind of execution that one expect in this language. So you see that this input, depending on the input, the behavior changes. Okay, and then also through not the outcome of the execution that can be produced in the during the execution, in the middle of the execution, like 62, which is an output, 25 is another output, and so on. So another example is this program. So it's very similar. We say x 124, and then we declare, and we say y is equal to 0, and we declare new var. X becomes 3, but inside the new var we call fail, and then we set the value of variable y is equal to 2. So for this program, now what's the output of this program has to be? I mean, what in terms of execution, the control flow, we know what's going to happen when x gets assigned to 124. After that, y will receive value 0. And then local variable x will be initialized 3. Because of this fail, program terminates. When it terminates, it produces some state as a result. Okay, instead of just, if it fails, it doesn't do anything, it dumps the states at the point of the failure. Now the question becomes, what kind of state should be returned? So whatever happens, I mean, this guy will never not execute it. But the question is, what kind of output state has to be? And then the output states, in this, the kind of output state we expect is x has a value 124, and then y has a value 0. Now, this is different from the case where x has a value 3 and y has a value 0. I mean, the second option may happen because if the execution goes into x becomes 3, if we call fail before restoring the value of variable x, program just stops and then return what we have at the moment. So then this second output can also be a possible option. Okay. But what we're gonna say, this is not what we want. The one above is what we want. Okay. Why is that? That's because if the value of a local variable start to influence the result of the entire program, then we may be in trouble. I mean, this means that renaming of local variables preserve the meaning. Okay, so for instance, instead of x gets 3, if we replace it by y gets 3, so we rename the value of local variable. In that case, the similar kind of execution is going to be x has 124 and y has a value 3. Okay, So we will get the one below. This is also not what we mean. So you see that we get different outcome depending on which name we use for the local variable. And that's not what we want. So we will look for semantics that does not give us this option 2 and 3. Instead, it gives us the option 1, which means that it will restore the value of global variables even when in the presence of the failure. Okay, so that's what we're gonna do on Wednesday, and we will look at the semantics of this language on Wednesday. Okay, so that's it for today, and if you have any questions, you can ask me. I'll be around here for about 5 minutes. Okay, so thank you very much.